Okay. Are all of you a designer or a contractor or consultant or just all of that? Designer, please. Okay, good. Just 5 or 6. So contractors and consultants. Okay. Whatever you are engineers, right? And I think I would like to talk about what engineering is first before we get into the session so that we have a common understanding. First of all, have you ever asked what engineering is about? We don't use science. The definition of engineering is someone, the definition of an engineer is that someone who uses the scientific method to solve the problem. We don't use science directly, we use scientific method. Okay? So that means we are here today, we're going to talk about structure. So that means we are going to use the scientific method to do something with the structure. So the first question is, when do we need the structure? I suppose most of us build buildings, right? We don't build dams here because dam cannot be built by steel. It's gonna get rust. So we are here because we want to build buildings like this. So buildings need structure to withstand the loads. Correct? So our job as an engineer, or more specifically a structural engineer, is to provide a structural system for buildings so that that system can withstand the load and the building can stand safely. So that is our job. And you can see from this picture that we have two main groups or main categories for the load. The gravity load, which is the vertical one, and the horizontal load. Okay, so before we get into that, we now know that as an engineer, we need to provide the structure to withstand the load. So we have two sides, the loading side and the structure side, and which sometimes we call that the resistance side. Okay, so we have the loading that tries to harm our building, and then the resistance side, the structure that we need to provide so that our buildings are safe. Now, on the loading side, do we actually know how much the load is that is going to act on our structure? No, we don't. We can never know exactly the amount of the load that will act on our building. Correct? So we have to approximate it. I thought about this word this morning, but we have two words for it, approximate and estimate. But in terms of structure, we rather use the word approximate, right? In terms of price and cost, we use the estimate. Well, I don't know why. They seem very similar. But anyway, we would never know the load for sure, how much it is going to be. So we need to approximate. If it was science, you would need to try to find a way to measure the load to the very, very, precise digit. Okay, so this horizontal load is this much, which in the real world, I don't know if we can, but we are not going to because we don't need to. It's too pricey, it's too much. We don't need to know that exact amount of load acting on our building. And on the resistance side, do we actually know how much our structure can withstand the load to the very, very exact point? No, we don't. We will never know. Let's get started with the things that you are most familiar with, the reinforced concrete beam, all right? You know that have you ever thought about concrete this way? Actually, steel is homogeneous material, right? So in fact, in terms of materials, it's easier than concrete because concrete is a composite one, which requires two materials to work together. So we have so many rules. For example, you need to change the steel into, the equivalent concrete area and sort of thing before you could use the assumption to design one reinforced concrete beam. So do you actually believe that those assumptions are correct? and very precise, give you the accurate answer. If you believe that, I believe you need to study science, not engineering, because you're gonna go crazy. There is no way in the world that you can tell that how much this beam can carry moment, or how much moment that beam can carry, right? Sorry, bad grammar. You will never know. So we need to approximate. And if you can recall your concrete day, you know the end that you use to change the steel, the reinforcing steel into the equivalent concrete, how much is it? N equal to 8, 9, 10. So you have the homogeneous section, right? And concrete itself, is it homogeneous? No, it consists of some kind of aggregates, rock and sand and water and cement. So how could you estimate or approximate the strength of material like that? Sand, rocks, water, cement. How could you go directly to one column? FC prime is equal to 257.2 kilogram per square centimeter. We could never do that, and we don't have to do that because we are engineers. We approximate it. Okay? And now there are two sides. The first is the side of the load that we will never know. We need to approximate that as well. And the second side is the resistance side that, again, we need to approximate the strength of the structure. So can I try to switch this into the camera, right? Will it work? Oh, yes, work beautifully. Okay? So you have the load side. And then you have the resistance side. Correct spelling, right? Okay. On both sides, we need to approximate. But our job, our simple job as an engineer, just to make sure that the resistance side is always greater than the load side, right? If this, operation is on the opposite like that, oops, right? We cannot allow that to happen. Now on the load side, you know that this is pretty much governed by what we know as the law, the municipal law. Okay, in Thai we call that กฎกระทรวง or whatever, พระราชบัญญัติ, the act. Okay, so that means one of the jobs that we need to do just to make sure that our building will satisfy the loading condition according to the law. But as an engineer, the law is just some sort of prescription that you need to follow as a minimum requirement. Okay? So that means if the law says you have a building and it needs to be able to withstand the live load equal to 200 kilogram per square centimeter, if it is an apartment, that is the minimum requirement. If you as an engineer feel that 200 kilogram per square meter, not centimeter, sorry. If 200 kilogram per square meter is not enough, it is not safe for this building because you know that according to whatever the events in the future, 200 may be too small. You as an engineer need to adjust that. Okay? Even the law says 200, but you as an engineer should know better. So if you think you have to do more, you will do more because the law is only the minimum requirement. Okay? And now whatever you do, you need to satisfy that at the least. But we are not here to talk about the law today because I think this is a gimmick and there's not much in it. And no matter how much we talk about it, there's nothing you can change with the law. So we are here today to talk about the resistance. Now, if some of you have read the technical paper before or may not, actually, when we try to calculate or approximate the strength of the structure, actually the general word I would like to use is that we predict the strength of the structure. You see, to calculate means the answer should be correct in some perspective, right? But if I say predict, it means that we will not really know how much we have. So when I do the research and I have the strength from the approximation based on the lab results or the test results and so on, the word that I should use is the predicted strength. So whenever I try to publish something or when I talk to my advisor, when I wrote my dissertation, this is the word I would use. It's something that we could never know, so we predicted. Okay? And from the predicted strength, there's so many good people, very smart people, would try to come up with a set of equations that we can use to predict the strength of our structure. Right now, for the entire day, you will see the formulas that they suggest us to use to predict the strength of the column, the strength of the tension members, the strength of the beams, and so on. We predict. Okay, so that will not give you the exact number of the strength at all. So from now on, please keep in mind that everything we do, we predict. Okay, but we predict according to smart people. So they tend to get it right. Or not right, just say satisfactory. Okay? Now, from the predicted strength, there's another name which is pretty much equivalent to that. I begin with this word so that you know that whatever we do, all the numbers we have, they're not really the exact answer to the strength of our structure. Okay? Whether you are a contractor, whether you are a designer, whether you are a consultant. Okay. Generally, from the calculation, the word that I should use is this one. So we will be familiar with this one. They call nominal strength. Okay? So if you look into the dictionary, the word nominal will give you a lot of problem because I don't really know what it means. But the general meaning of the word nominal strength is the calculated strength. It's whatever it is, it's something that we get from the calculation using those equations suggested to us by, say, the committee, the very, very good, smart people. Okay? So that is called the calculated strength, nominal strength, the strength that we can calculate from the formulas. But going into the real world, we could never really use the calculated strength because there are so many things that we call uncertainties. Okay? So uncertainties are things that we cannot really say how or how much things are going to happen. That's why it is uncertain. And so there are uncertainties on both sides of our work. The load is uncertain by itself. You know that you could never really tell how much live load in one room is going to be, correct? Let's say we have like 40 people here and perhaps this room is designed to withstand a live load, maybe 400 because it is a public place, but this is not 400. And even so 400, maybe can we have the load to exceed 400 one day? Perhaps, right? Let's say that's a flood event. And this turns out to be a shelter for people. So, you know, people just bring the stuff in, the logistics and the rice and food and so on, they just pack in this room. So that's a chance that the live load may exceed 400 as well. That is the uncertainty of the load. What about on the resistance side? We also have uncertainties. How do you know the material you use will have this and that much strength? You don't, right? That's why we send some materials to the lab to test. Even with the test, how could you tell exactly? You can. How much the size of the beam will vary from what you design. If you design a concrete beam like maybe 20 by 50 section, and after you cast the concrete, are you sure that it's that big? So there's so many uncertainties on both sides. And before we really tell if our structure is going to be safe, we need to incorporate those uncertainties into our calculation or our prediction or our approximation. Okay? That is engineering, ladies and gentlemen. Okay? We approximate things to our best abilities. And actually, there is one, say, feel-good word that they use. They call it an estimated guess or educated guess. Educated guess, right? If you guess with good education, something like that, you guess based on reasons. That is why the definition of engineering is that we use the scientific method. That is scientific method, ladies and gentlemen. We use it to predict the strength of our structure. We use it to try to evaluate the load and approximate the load that will act on our structure. Okay, so whatever we're gonna do from now on, let's just say that everything is approximation. Okay. Now, I generally, whenever I go, I will always talk about the steel structure based on the new design specification. And I suppose some of you know that already, that right now the AISC, which is the specification that we use, and Engineering Institute of Thailand also, create the standard based on that as well. Right now, they have unified the ASD and LRFD into one group of formulas. So no matter what you choose to do, ASD or LRFD, all the formulas that we will use to evaluate, approximate, or predict the strength of our structures will be the same set of equations. Now, it doesn't differ from what we have here. It's just the load side and the resistance side. Okay, but now we have the same set of formulas. So before I get into the details, let me clarify this first. Okay, right now in the old days there used to be two design approaches, but now still two design approaches, but they use the same formulas. The old one is ASD and LRFD. So if for some of you who are familiar with the OASD, the S here stands for stress, right? For ASD 89, this is stress. But when they unify, they no longer use the stress because it doesn't work in some cases. So the new ASD S stands for strength. Wow, what a coincidence, right? They don't need to change the name. But they don't use this anymore, ladies and gentlemen. So the new ASD stands for allowable strength design. Now, whatever you use, ASD or LRFD, we shall have the same set of equations to predict the strength on the resistance side, which is it's too big. Yeah, okay. Yeah, the resistance side is on the right side, okay? And this is the load. So let me write it down again. Load and resistance here. Okay. Now for ASD, on the load side, you should be familiar with what we call the service load. Okay? And the service load, please keep in mind that you need to use load combination, okay? You need to combine date load and live load and water and whatever to find the worst case scenario that could happen to your structure, and then you design for it. Okay? So that is the service load for ASD. The service load means that you just take the load as it is without increasing it by using any factor. So the service load, another name is unfactored load. Okay? We don't multiply the load with anything. Okay? And on the strength side, we will use the nominal strength, okay, which is the strength that you can calculate from the formulas. But we cannot use it right away, so we're going to use the nominal strength and then divide it by the factor of safety or omega. Okay? And you compare this and make sure that, again, the nominal strength divided by factor of safety is greater than the combination of the service load. Now, on the other hand, the LRFD will be concerned about the uncertainty of the load in the way that they will use the factored load. Okay? So you'll be familiar with this. For example, 1.2 date load multiply up 1.2 multiply the date load plus 1.6 multiply the live load. We increase the uncertainty on the load side because you never know what's going to happen. But in the meantime, you're going to use the nominal strength up to almost, its maximum. We're going to use it actually to the maximum, but we cannot be sure about the strength either. So we will reduce it a little bit by the phi factor. So it's a nominal strength multiplied by the phi factor. And right here, this is called the reduction factor. Okay, so they are, the same and different at the same time. They use a different concept. ASD, they just, take the load as it is, but you are not allowed to use the strength up to maximum. You just make sure that everything is safe by simply including the factor of safety in your calculation. And that is ASD. Okay? For the LRFD, we take care of the uncertainty on the load side by increasing it using the factors. So we have the load perhaps more than the normal number. But we're going to use the strength as much as we could as well, with some deduction to account for the fact that we don't actually know, say first, how big your beam is. Even though it is a hot roll, a standard steel section coming out of the manufacturing process, you will never know the true thickness of the flange, for example, or the true thickness of the web. So we need to account for that. Or we don't even know if the formulas we use will actually work the way it's supposed to. So we account for that. Now, ladies and gentlemen, in general, because no matter what design approach you use, it still behaves the same. So in general, whether you use ASD or LRFD, you should get the same results. Okay? Now, anyone who comes in touch with me in my life, they should know the story behind this, and so should you. Okay, generally, when we consider the load side on the ASD, the service here and say ASD, and then LRFD. This is a factor. Generally, check area monitor to display. I just did, huh? I think he wants to speak English as well, right? Okay. Generally, this is 1.5 times different. This is the magic number that they use when they want to develop two different design approaches. So that means on the resistance side, when you consider the factor of safety and the phi factor, when you multiply this together, the number is always 1.5. That's the magic number behind it. If you ask me why 1.5, I don't know, because there's some very, very smart professors who have done the work on statistics and so on. Then they come up with this magic number. So that means on the resistance side, the ASD is 1.5 times less than the LRFD, but on the load side, it's the same. So that means if you use the ASD or if you use the LRFD, generally you should get the same steel section. Now this is true until this. This is true as long as the ratio of live load over date load is not more than 3. Now, ladies and gentlemen, anyone who, comes across myself must know this. 1.5 and 3. So that means if you are handling a typical steel section with the live load no more than 3 times the date load, whether or not you use ASD or LIFD, you should always get the same size of the section. If you get different, that means something is wrong. Okay? But if the live load becomes so much more than the date load, exceeds this magic number 3, the LIFD will begin to give you a bigger structure. And if you ask me, it makes sense because the LIFD put a lot of emphasis on the uncertainty of the load. So if you have a very, very large live load, how can you be sure about it? You would rather provide the structure on the safe side, right, than become sorry later. Better be safe than sorry, they say. Okay? So that makes sense to me. But ladies and gentlemen, now that we talk about this, I should talk a little bit more about what you should do in our country as well. Okay? Keep in mind that the load side is the law, right? As I mentioned earlier. So that means if you design the structure in this country, you're going to have to abide by the law in this country. If you somehow handle or are a consultant of the structure built in our neighboring countries, such as Cambodia or Myanmar, you need to be aware of their laws. You cannot say, sorry, I don't know, I'm from Thailand, I don't know the laws in your country. You cannot say that. It's your responsibility, right? And that is the load side. And when you face this, you need to make a decision. Now, but for our country, currently, there is no law covering the LIFD. There's one general, say, law about the load combination of the ultimate, but that is for concrete, ladies and gentlemen. The notorious 1.7 date load plus 2 live load. And notorious is always a bad thing, right? Yeah, so some of you may already know this. If you have to handle the ultimate strength design in concrete and you have to abide by the law, you have to face that crazy 1.7 date load plus 2 live load because it's a law. But if you read more carefully, you see that is only for concrete. So we don't have that for steel in Thailand. But you now know that as long as the ratio of the live load and date load is not more than 3, it doesn't matter which one you use. And you can still use ASD just fine. And you will perfectly abide by the law and the Act of Thailand, the Building Act of Thailand. Okay? So I think we get the concept out of our system. Is there any question, ladies and gentlemen? Or they would know that I have my signature phrase. We are crystal clear, right? Then we can move on. Okay. So that's that. So now you should know whatever we do, whatever we talk about, it's pure approximation. So don't go crazy with formulas and numbers, okay? So this is the building system that we have seen, that your structure needs to be able to withstand both the vertical load and the horizontal load. And you need to take care of that. You need to study the law. You need to study the standard and make sure that whatever the load that you use to design your structure will be in perfect agreement with the law. Okay? And that's just the example. I'm not going to go into details. Just an example of the minimum requirement for the load from some country that they have so many things for so many types of buildings. And you know, I don't intend to go into details of the concept of statistics that bring the formula to us, but it's worthwhile that we take a look at this for a while. You know, it's crazy enough that some curriculum doesn't have statistics in the curriculum. So, did you have statistics when you were an undergrad student? No, you didn't, right? Right. It's just because that was the curriculum before I arrived, and when you don't know about statistics, it's not the end of the world, but it doesn't give you, say, some sense that whatever we do is based on statistics, right? Because as I said before, we don't know what's going to happen. We take samples from the concrete, right? 3 samples. How do you know it has to be 3? Somebody tell you 3 samples. Take 3 cylinders to the lab and then just smash it to see how much compressive strength it is. Then how do you know those 3 cylinders can tell you the strength of the concrete of your building? Says who? It's purely statistics, right? It's just like flipping a coin and ask you, it's going to be heads or tails. And you know it's 50-50. We know that. That's statistics. But that is called discrete statistics. You can tell it's either head or tail, right? But there is a statistics called continuous statistics, which comes out to be a Bernoulli normal distribution curve like this. And we use things like this to try to come up and say, okay, that's how we know we can use this number for the live load in the apartment. It comes from this craziness, you know. But all the smart folks have taken care of this for us, so we can just, okay, 200, I'm fine, I can use this safely. Because so many good people have done this, I don't want to say dirty work, but it's kind of very, very hard work and hard calculation. Use some crazy integration, calculus, Laplace, Fourier, and then one day, okay, 200 for apartment. I'm not joking, ladies and gentlemen. This is true. And people have done the dirty work for you so that you can just 200, 250, 400, and so on. And this is the dirty work that they have done. It's just 2 normal distribution, and just to say that, okay, the normal distribution, which is the statistics of the structure, should always be greater than the load. Right? So that if you look carefully, somehow I cannot get the cursor on this, but if you look carefully, this is the region where the load is greater than the resistance. So that is where the failure may occur. That's not nice. So our job is just to make sure that your graph here is always beyond the load. Okay? And we take care of that by using both the factor of safety in ASD or the reduction factor and the factor that you use to increase the load for the LRFD. So that's the general idea of whatever we do. Okay? And again, statistics that the frequency of the load that they used they try to accumulate all the data and then calculate so that you have the magic number. It's just another example. And this is another example of the uncertainty of the steel structure. You see, that's the dimension that you will see from the steel table, correct? The height of the steel section, the width, which is B, and then this is the average value of how much the measurement is deviate from the size that you look from the table. So see, it's never going to be exactly the same. So we always have the deviation, and therefore we must always use statistics, because we will never know. and statistics is the really badass. It's very difficult. I came across that once when I was doing my PhD, and then I remember my instructor. He's a very nice person. He's the nicest person, one of the very nicest person on earth. Even with the exam, it's a take-home exam. So I guess he could do that because it's just like 2 students in the class, and because the subject was so hard, just 2 students, and then I did something, and then I the take-home exam, and I gave it to him, and he looked at my exam. Apinat, that is wrong. Go back and fix it. It's the exam, But that was the first time that I realized that you go to school to learn, not to have somebody tell you you're wrong, right? But most of the time when we are in school, in some country around here, I don't want to mention, teachers only say, you're wrong. And when they say you're wrong, they kill you because you no longer want to share your opinion with your friends or your teachers. Okay? You only know how to follow them. So the GPA in the school would generally mean conformity and obedience. Students with good grades mean they go along well with teachers. But that doesn't mean that every student with good grades are bad, But students with good grades, they are conform with their teachers very well, which unfortunately not me. Anyway, so that's the point. Okay, and you can see that the average of the ratio and then the standard deviation. Say even the section that is manufactured from the factory, they still have deviation, and that's why we need statistics. And for the LRFD, I'm not going to go much into details because you will hate it. And I don't really use it in my everyday life, so I don't remember much about it. But this is it. It's about the calculation of statistics. They take the natural logarithm and the great Bernoulli, I don't know which one, because the Bernoulli is a very big family. Some of them create the equation for the aeroplane. Some of them create the equation for beams and so on. So one of them create this distribution for statistics, and they use the natural logarithm function to make sure that we have the beta, the index, and the reliability issue.